All right, so for this daily bonus number 42, write down some clever way of memorizing the 6 strong acids. Well, I'm not going to do that part for you, but you need to come up with some way where you can know that for the purposes of this class, these 6 acids are the strong acids, and everything else then is considered weak. So for number 2, explain why it's acceptable to assume that the concentration of a strong acid is equivalent to the hydronium concentration for that solution. Well, if you take one of these strong acids like HCl and you dissolve it into water, it's going to be a one-way reaction. Every bit of this HCl is going to dissociate into hydrogen ions and chloride ions. There is no reverse reaction because none of these ions come back together to form HCl. So if you put in 0.2 mole of HCl, since it's a 1-to-1 ratio, you're going to get out 0.2 mole of H+. And each one of those H+ ions is going to attach to a water to form hydronium. So for all intents and purposes, H+ concentration is the same thing as H3O+ concentration. So if you know the number of moles of the acid going in, the strong acid going in, you're able to find the concentration of that. Since it's a 1-to-1 ratio, the concentration of that strong acid is also going to equal the concentration of the hydrogen ion concentration, which will then also equal the hydronium ion concentration. To make a long story short, because since they entirely dissociate, you are able to assume that the concentration of the hydronium is the same as the concentration of the strong acid. For number 3, consider a 0.02 molar solution of HCl and find the following 4 things: the hydronium concentration, the hydroxide concentration, the pH, and the pOH. So let's just start with the hydronium concentration. Again, we've got HCl. It's a strong acid. It's going to fully dissociate. If we have a concentration of HCl of 0.02 molar, then that means if that equals the concentration of the HCl, that also equals the concentration of the H+ ions, which also equals the concentration of the hydronium ions. So pH equals negative log of the hydronium ion concentration, which we just said the hydronium ion concentration is 0.02. So we're simply taking the negative log of 0.02, and pH equals, let me get my handy dandy calculators, negative log of 0.02, and we're kind of just ignoring sig figs. Well, not really, I guess. This has one significant digit, so our pH will be 1.7. Again, remember on pHs, the number before the decimal is just a magnitude. It doesn't actually show any significance. So this pH of 1.7 has one significant figure. Now, I just randomly chose to start with the pH, but I accidentally, without saying it, also answered the hydronium ion concentration. It's going to be the same as the concentration of the HCl. So we really just answered 2 questions at once. So let's clear some of this off. As you watch me erase this, I just hope you're having a fantastic day. And let's make some notes here. We said the hydronium ion concentration was 0.02 molar, and the pH was 1.67. Now, I'm going to go ahead and find a pOH next, just because that's easy to do. pH plus pOH has to equal 14. So if you rearrange this, the pOH then must equal 14 minus the pH. So 14 minus our pH wait a second, our pH wasn't 1.67. What am I thinking? Our pH was 1.7. So we take our 14 minus 1.7, and we find we have a pOH of 12.3. So now you have 2 options whenever we go to find this OH concentration. You can either say that 10 to the negative pOH equals the OH concentration, meaning raise this power, or take 10 to the negative 12.3 power to find your OH concentration, or you can say since Kw equals the hydronium concentration times the hydroxide concentration, we know Kw, it's 1.0 times 10 to the negative 14th. You also know the hydronium concentration because we already solved for it. So you could plug that in here and solve for OH. That's the second option for finding the OH concentration. That sounds entirely too laborious to me, so I'm going to use this option right here. 10 to the negative POH, which is 12.3, is going to equal our hydroxide concentration. And in this case, 10 to the negative 12.3 equals to 1 sig fig, 5 times 10 to the negative 13th molar. For part 4, you're given a solution. Solution A has a hydronium concentration of 3.5 times 10 to the negative 5th. Solution B has a hydroxide concentration of 4.2 times 10 to the negative 9th, which is more acidic. So you're comparing apples to oranges here. You need to either convert these both to pH, both to POH, or something. You have to do some sort of conversion here to be able to compare these. So for solution A, again, Kw equals the hydronium concentration times the hydroxide concentration. We know Kw, we know for solution A the hydronium concentration, so we could solve for this hydroxide concentration. Well, Kw is 1.0 times 10 to the negative 14th. The hydronium is given right here. It is 3.5 times 10 to the negative 5th. And we don't know the hydroxide concentration, but we can divide now both sides by 3.5 times 10 to the negative 5th. When you plug this into your calculator, you need to be careful and put the denominator in parentheses. So let's plug this in. Your hydroxide concentration, when I plug it in, I got to 2 sig figs, 2.9 times 10 to the negative 10th molar. Okay? So now from here, you could technically answer this question. We have the hydroxide concentration of solution A, which is 2.9 times 10 to the negative 10th. That is less than this hydroxide concentration from solution B. That means that solution A has a lower hydroxide concentration, which means it must have a higher hydronium ion concentration. If solution A has a higher hydronium ion concentration, then solution A is more acidic. If you don't want to work it that way, you could also think of it in terms of pH and answer the question that way. So let's try that. If I just wanted to find the pH of solution A, I'm going to take the negative log of 3.5 times 10 to the negative 5th. So negative log of 3.5 times 10 to the negative 5th in my calculator. This has a pH of 4.46 equals solution A's pH. Now, if I took the negative log of 4.2 times 10 to the negative 9th, ignore the bell, then negative log of 4.2 times 10 to the negative 9th, I find that that equals 8.38. But you've got to be careful here. You just took the negative log of the OH. So you did not just find the pH here, you found the POH. So, again, you're still comparing apples to oranges. We've got to get these to something that's common. But like we just said, 14 minus 8.38 will get us our pH. And in this case, that is, math is too hard for me, so I'll just plug it into a calculator, 5.62. Now we can tell this has a pH of 4.46. That is more acidic than solution B. And last, for number 5, very similar to the option we just did, we've got the pH of a solution that's 12.11. What's the concentration of the OHs? Well, 10 to the negative pH will tell us our hydronium ion concentration. Once we know our hydronium ion concentration, we could use our Kw expression, 1.0 times 10 to the negative 14th equals the hydronium ion concentration times the hydroxide ion concentration. Doing it this route, you would be able to find this hydronium ion concentration, plug it in here, and then ultimately solve for the OH concentration. Or you could tackle this from a pOH standpoint. 14 minus 12.11 is, again, math is just simply too hard for me. I guess I'm too hungry. It is 1.89, and that is the pOH of this solution. Then 10 to the negative pOH is going to equal your OH concentration. And that method just seems easier to me, so I'm going to do that. I'm going to say 10 to the negative pOH, so 10 to the negative 1.89, 10 to the negative 1.89 gets me a hydronium ion concentration of 0.013 molar.